So in this lesson I'm going to tell you about an atomic force microscope, which is a conceptually very simple instrument, and talk about what makes it so interesting, and that's primarily its resolution, which is much better than one would expect from the simplicity of the concept. So what is that concept? Well, if we take a small, thin device with a very sharp tip, shaped much like a diving board, we call this a cantilever, and we shine a laser light down on it. Well, it's at an angle on that's reflective back surface of the cantilever, so the laser light bounces off, and it shines onto a quadrant photodiode. Well, each one of those sections of the photodiode is able to generate a voltage, depending on how much light hits it, and as cantilever moves up and down, that light spot also moves up and down. And so the very simple premise is that you send the signal from the photodiode to your computer to track the motion of that cantilever, which has the sharp tip on it, and if the tip is near or touching a surface, and you have means to move the cantilever and the sample relative to each other, you can move one or the other, it doesn't matter, then you can get an image of that surface by plotting the motion of the cantilever as represented by the voltage from the photodiodes as a function of position, the relative position of the tip of the sample. So you might ask, well, why are there 4 quadrants for the photodiode, and not only just like top half and bottom half representing the up and down motion? And that's a very good question. So if we take a look down the long axis of the cantilever, it would look like this. And any laser light coming up would just sort of be reflected straight up from this perspective. But if we had the cantilever at a slight angle, say something like this, and that would indeed happen if we're moving the cantilever this way, then the laser light reflected is going to be coming off at a much different angle. And if we had the cantilever in motion in the other direction, say like this, then guess what? The laser light comes off at an angle going off to the right there. So not only can we track the up and down motion of the cantilever, we can also track the twisting of the cantilever by seeing that reflected light spot going back and forth instead of up and down. So this gives us quite a bit of power to track surface features and friction with the surface. And it's really quite interesting that such a simple idea gives us some very, very good resolution. You might remember that the wavelength of red light is about 600 nanometers, and the wavelength of blue light is about 400 nanometers. And it's only when you get to about 10 times wavelength are you able to see something. So that means in optical microscopes you can see some microns, but you can't see much smaller than that. And whereas with an AFM, the resolution of AFM vertically, it's on the order of 1/10 of a nanometer. In terms of the force it can detect, that's on the order of 1/10 of a nanonewton. And a typical contact area between the tip and the sample is on the order of 10 nanometers squared. So why is the vertical resolution so good? Well, let's first imagine that we're moving the cantilever up and down like this, and shooting the laser light down. We're not changing the angle, so the laser light would come off in parallel here, and that goes up to the photodiode. Turns out we would have to move the cantilever about a micron in order to see a voltage change on the photodiode. So that's not the key. The key is that the cantilever changes its angle like so as it moves, and of course I've greatly exaggerated that. But when we think about the reflected light, what we want to do is think about the normal to the surface, i.e. perpendicular to the surface. And you probably remember from your distant past that the angle of incidence is equal to the angle of reflection. And that hasn't changed. So if we shoot laser light down like this, it's going to come out like this. And for the other one, if it hits like this, it's going to come off like this. So this angle here is equal to that angle there. This is the angle of incidence. This is the angle of reflection. And this is what gives us this wonderful sensitivity on the order of 1/10 of a nanometer. And if you remember, 1/10 of a nanometer, that's 1 angstrom. And that is 1 diameter of a hydrogen atom. So that is really, really small. It is 10 billion times smaller than a meter. So let's do Hooke's law. Hooke's law expresses the relationship between force and deflection. They are proportional to each other by a constant called the spring constant. And what's the deflection? Well, here, if we have our cantilever, and if it comes in contact with the surface and it bends backwards, then the amount that it moves is called the deflection, or D. And I typically use this, or measure it in nanometers. At K, the constant, is called the spring constant. It is measured in newtons per meter. There's quite a range for that value. It can go from as little as 1/100th of a newton per meter on up to about 100 newtons per meter. And 100 newtons per meter, that's about the stiffness of the spring in a ballpoint pen. A newton per meter, that's about the stiffness of the child's toy called Slinky. And 100th of a newton per meter, that is very, very compliant indeed. Where does that control over the range of spring constants come from? Well, we make these cantilevers using the same technology used to make accelerometers that deploy the airbags in your car, and also that go in the handsets in your video games, and as in iPads as well. And that control over the spring constant, forwarder's magnitude there, depends mainly on the ratio of the thickness to the length. So the thinner it is, the floppier the cantilever is. So if we take some typical numbers, and let's take a newton per meter for the spring constant and 1/10 of a nanometer for the deflection sensitivity, as we were just speaking of, then the force resolution that we would get is tenth of a nanonewton. Now, a tenth of a nanonewton is a factor of 10 to the 11 times smaller than the weight of a 1 kilogram object. And just to give you a sense of how small or how big 10 to the 11 is, if we take a meter and we multiply it 10 to the 11 times, we have not yet reached the sun from the Earth. So we have very, very good force resolution with atomic force microscopy. Now, what about the aerial resolution? Well, it's a little bit beyond us right now, but let me just tell you why that's important. Here we've got an AFM tip in contact with a surface, and the manufacturers typically claim that the tip radii are on the order of 10 nanometers. And that's probably true when you get them out of their box. But one good whack on the surface, and you've got some really, really high pressures between the tip and the sample, and something's got to go. And interestingly, it's not the force that controls the damage to tip or sample, it is the pressure. Pressure is force per unit area. Now, we want the area small because that way we can measure small features, things we can't see with an optical microscope. But look, the area is in the denominator, and so when that gets small, the pressure gets really high, and we don't want the pressure to be high because that's really what causes damage. And so the only way we can be successful at imaging small features is that we keep the force small. So the force must be small in AFM. But, well, what have we just been talking about? We've been talking about how we can measure small forces because of our very good control over spring constant and over deflection. So it's going to work out. So typical numbers again, spring constant of a Newton per meter. Let's take a deflection of a nanometer this time. And it turns out that these areas can be as small as 10 square nanometers or so. So this works out to 10 to the minus 9 in the numerator, 10 to the minus 17 in the denominator, and that leaves us with 10 to the 8th newtons per meter squared for pressure. Now that is a high pressure, but many materials can withstand it. You would find that pressure at the base of a skyscraper, for example. And so that's how we can measure very small things in an atomic force microscope, is because we have very good deflection sensitivity and very good force sensitivity, and therefore we can control the pressures such that we can image very small things without damaging them. So in the next lesson, I'll show you some examples, and you'll get to see some AFM images.